Okay, moving to the next part of this WMO report called United in Science 2022 is on greenhouse gas concentrations. Some new information, or at least the way it's presented, some of it is something we have looked at under carbon cycle, climate change, and so on, but it doesn't matter. So atmospheric greenhouse gas concentrations come from WMO Global Atmospheric Watch Program. I think everybody knows World Meteorological Organization sits under, I think, UNESCO, and then it also runs the IPCC coordination of all the scenarios which produce the assessment report, and they run the World Weather Research Program, the World Climate Research Program, and so on, and they have Global Energy and Water Experiment, various programs which work at global levels and coordinate scientific activities, plans, strategies, observation systems, and such. Key messages from greenhouse gas concentrations is concentrations of the major greenhouse gases continue to increase in 2021 and the first half of 2022 when the report was finalized. Overall emissions reductions in 2020 did not have a substantial impact on the annual increase of the atmospheric concentrations of long-lived greenhouse gases. The role of carbon uptake by the atmosphere in achieving carbon neutrality would be better understood if supported by more robust atmospheric observations. Data can never be enough, and WMO and its programs tend to try to plan, optimize networks, coordinate international efforts, funding, and so on and so forth. But obviously, over the ocean, there is very little coverage. For example, on land also, it's not as good as it could be, or should be, or needs to be. Okay, so just looking at some of the observed concentrations, our favorite killing curve is here. As I always point out, despite the 25 years of negotiations, we still don't see a reduction, or the at least the reduction in the rate of increase of CO2. It's going at I think more than 4 ppm right now. And you can take differential of this and produce growth rates, which is done for CO2, methane, and N2O here. So you can see that the growth rates have ups and downs depending on other modes of natural variability, or wildfires and El Nino and La Nina, etc. So globally average CO2, methane, and N2O mole fraction in ppm and ppb. For methane and N2O, obviously it's ppb, whereas here it's ppm, and its growth rate in the lower row from 1984 to 2020, so more recent period. Observations from 139 stations were used for the CO2 analysis, 138 stations for methane analysis, and 105 stations for the N2O analysis. The red line in the top row is monthly mean with the seasonal variation removed. So this breeding of the planet, photosynthesis, etc. has been removed. So you can clearly see the trend riding under that. The blue dots and lines depict monthly averages. So you can see the dots in this curve that's going up and down. Increases in successive annual means are shown in the shaded columns here. So growth rate, basically you can see the rate in ppm per year, ppb per year. So as I said, we are somewhere here in the range of 4 and down now just under 3 by 2020, but 2021, 2022 we have shot up again. So the uptake uptake, sources, sinks, everything is included to look at how growth rate in the atmosphere is changing. Methane is a more complicated story. It has had ups and downs which are not always fully understood, and you can see that sometimes there is a impact of the financial crisis and so on. So in ppb per year, it remained at 10 to just about 10, and then dropped during the 1990s, and then had ups and downs and dropped again in 2000, and now it is headed back up, which you can see here, the flattening here, which shows as the reductions in growth rates. N2O mole fraction in ppb shows pretty much a steady increase, just like the CO2. Parts per billion is much smaller, but what we have to worry about, of course, is their residence time. So this is multiple centuries. This is a decade or so, and we also have to worry about their global warming potential, which is, this is about 25 times CO2. This is I think a couple of hundred times CO2. You can check it. So you can see that the growth rates here, like CO2, also show an increase in the 21st century. So these are to be kept in mind. Global greenhouse gas emissions and budgets from the Global Carbon Project we have looked at elsewhere. The key messages from there are that the total anthropogenic carbon dioxide emissions were estimated at 38 gigatons CO2 per year in 2020, with a preliminary estimate of 39.3 gigatons CO2 per year in 2021. So slightly up there. Preliminary data show that global CO2 emissions in 2022, January to May, are 1.2% above the levels recorded during the same period in 2019 prior to the COVID pandemic. So we are recovering from the slowdown in CO2 emissions that happened. And these do not, this is CO2, does not include methane and N2O here. A quarter of GHG emissions from land use change are associated with the trade of food between countries, of which more than 3/4 are due to land clearing for agriculture, including grazing. Okay, land use change remains a major contributor. Looking at the annual absolute changes in global fossil fuel CO2 emissions, this is Pierre Friedlingstein's work, who leads these kind of global analysis every year. So here, going back to the 1900s, you can see there has been ups and downs. Great Depression, the associated slowdown of economic activities and consumption brought, for example, the fossil fuel consumption down. These are annual changes. World War II also had huge impact on industrial production, travel, consumption, production, everything. Second oil crisis here, which actually was supposed to make a change, but we bounced right back. Dissolution of the Soviet Union also showed up in the financial crisis, and if here you can see again we bounce back. Little dips happened, global financial crisis of 2008, and then COVID, of course. But now COVID pandemic had little impact on slowing down. Travels reduced, production reduced, consumption reduced, maybe, and so on. Post-pandemic rebound. So we are here back to post global financial crisis rebound kind of situation. So there are always this bouncing around of fossil fuel consumptions, which show up based on various other factors. Right now, for example, Russian war is having a huge impact on gas supply to Europe. We will see how that will show up as changes in fossil fuel CO2. Okay, unfortunately, more coal is being burned by some countries, of course. This is changes in fossil fuel CO2 emissions for the world and a selected group of countries for January to May in 2020, 2021 and 2022 compared with the same period in the previous year. So this is just to show what's happening. So 2020 versus 2019, 2021 versus 2020 and 2022 versus 2021, and you can see that 2021 is up here. 2022 is also bouncing back, and this is only part of the year compared to 2021. So obviously 2020 compared to 2019 was greatly affected by COVID restrictions and so on. This again we have looked at elsewhere. This looks at human perturbation of the global carbon budget average globally for the decade of 2011 to 2020. So this keeps getting updated. So there is 2011 to 2018, 19, 20. So the data is still behind. So 2011 to 2021 will become available at some point. Again, Pierre is leading this effort with a bunch of global carbon cycle experts. Shows the various stocks and carbon cycling in gigaton CO2 per year, and anthropogenic fluxes in thicker arrows for 2011 to 2020 average in gigaton CO2 per year as well. So you have various sizes of reservoirs here: gas reserves, oil reserves, and coal reserves. Obviously the big question is how to keep these assets buried in the ground, and we know coal is already kind of hopefully on the way down, except for bump ups from wars like the Russian invasion of Ukraine. Oil reserves are still being dug up, even CO2 sequestration. A lot of CO2 captured is used for enhanced oil recovery, and gas reserves. Usually it's argued that gas burns better, but you can have a rebound effect where you tend to burn more when something is more efficient, or and so on. Okay, so fossil fuel CO2 in the range of 33 to 37, so average of 35 over this period, and this is land use change 2 to 7, so slightly large uncertainty there, but 4 gigaton CO2 per year. Obviously we have to worry about permafrost, soils, and so on. There is 500 up and down for land use cover, so the differences tend to be small numbers between uptakes and outgassing, so we have to track them very closely, so uncertainties can be large. Soils store quite a bit. Hopefully they won't get perturbed too much, but with warming there is heterotrophic respiration that keeps going up as well. Permafrost thawing is a big concern, especially if it can have a positive feedback by releasing CO2 and so on. Turns out there are more complications because often lakes form, and lakes begin to have photosynthesis and some sequestering of carbon and so on. So one has to track the net over there. Rivers and lakes recycling, coasts and surface sediments, various stocks there. So budget imbalance overall remains at -1 gigaton CO2 per year. This is often called the missing sink, but this is reduced with great care in doing these things. But biosphere is taking up about 11 gigaton CO2 per year with a range of 9 to 13. Atmosphere is accumulating 19 gigaton CO2 per year, and ocean is taking up somewhere around 10 gigaton CO2 per year. So what else do we need? Ocean, of course, again, difference between two large numbers as to what is taken up by the biosphere and the gas exchange. Ocean, of course, has a large pool in organic carbon. Marine biota cycles a lot, so we have talked about biological pump and solubility pump elsewhere, and ocean has a big pool of dissolved inorganic carbon, much larger than all these except for the geological storage, which we are not looking at here. One can look at the airborne fraction. So this is fraction of anthropogenic CO2 emissions, which combines fossil plus land use climate climate forcing that remains in the atmosphere. So 1960 to 2021, you can see that there are ups and downs in the sinks, ocean and vegetation and so on. So basically it's settled down here with the 7-year smoothing. You can see that the airborne fraction of the total CO2 emissions remaining in the atmosphere is relatively flat. So total emissions are going up, and total accumulation in the atmosphere is going up. We are talking here about the fraction of the fossil fuel emission, anthropogenic CO2 emissions that remain in the atmosphere. This is kind of an interesting way to look at this in terms of global distribution of land use emissions embodied in trade between regions, looking at 2004, 7, 11, 14 and 17. One can look at the trends, basically timber and other products being moved around. Grains, land use emissions can come from agriculture, deforestation, etc. So you can see that China exports a lot, and but China is also importing a lot now. So this was in 2004. You can see that arrow has almost disappeared here. So the colors are here exported and imported amounts of CO2 in terms of million tons CO2 equivalent per year. So this includes other greenhouse gases as well here, methane, N2O, and maybe others like HFCs may be included here. One has to check. But obviously US used to import a lot, but has slowly reduced its importing of CO2, even though the scale doesn't show up as obviously here from 2004 to 2017. China's export to the US reduced, and this arrow is completely missing here, but interestingly China is taking a lot from Brazil and Chile and so on. So that's an interesting change here. You can see that this number and the arrow is quite massive by now in terms of the carbon that is being traded from here to there. And so China has basically become a net importer. Okay, India got drowned here, but it's also a net exporter or importer, I think. So numbers of US have dropped, but it is still quite red in terms of importing, and there are of course exporters, Russia and Canada and Australia. Australia exports lots of coal, so one has to be careful about whether that means the countries that are actually exporting are reducing their emissions or just exporting their emissions, right? This is what embedded trade always means. IPCC headline statements in the end: total net anthropogenic greenhouse gas emissions have continued to rise during the period 2010 to 2011. So that's from IPCC Working Group 3 AR6. Average annual greenhouse gas emissions during 2010 to 2019 were higher than in any previous decade, but the rate of growth between 2010 and 2019 was lower than that between 2000 and 2009. So there is some tiny bit of good news there. Net anthropogenic greenhouse gas emissions have increased since 2010 across all major sectors globally. So again from AR6. This is of course not good news. Okay, so we'll come back and look at global climate in the next podcast, the third part of United in Science report from WMO. Okay.